So once we found the proof that neither 1, 2 or 2, 1 contains a pit using the resolution rules and by hand, I want to tell that we could have applied any of the search algorithms we learned earlier to find a sequence of steps that constitutes a proof. We just need to define a proof problem using initial state, actions, result, and goal. Okay, so those are important. So we needed some initial state. Okay, initial state, because we have to draw our search tree. It can be the initial knowledge base. Okay, all the initial knowledge base statements can be combined to have the initial state. Then there'll be some actions. Okay, if you remember actions, which are the set of actions consist of all the inference rules applied to all the sentences that match the top half of the inference rule. So basically, so that will be the start state, the initial state or the initial knowledge base, and then whatever part matches on the left side, we apply the inference rule, and then we will get, those are the actions, we will get some next states. Okay, so then after that there will be something called the result. Okay, result. So result of an action is to add the sentence in the bottom half of the inference rule. So after applying the inference rule, whatever we are getting, those things goes back to the knowledge base. You add that sentence. And finally, you reach a goal. Okay, you reach a goal. The goal is a state that contains the sentence you are trying to prove. So for our example, the goal will be not P12. Initial state will be up to, let's say, R4, R5, whatever the knowledge base we had. If any other sentences you want to add. And the actions will be on the left part, whatever matches, let's say B11. When B11 is there, and you can apply, let's say, this by conditional elimination rule, and you will get an action, right? You will get this thing by conditional elimination. So you will get this thing. This will be added to the sentence, R6. Now after that, you can apply on the, so that will go back to the knowledge base. Then after that, on this part, you can, one of them you can apply another rule. So that way you keep creating nodes until you reach to a goal node. So the searching for proofs is an alternative to enumerating models like truth table. For all the variables, you add some true false value and then all possible combination until you find which one is true, your goal. So this is building the tree is also one way. Okay, in many practical cases, finding a proof using this tree search can be more efficient because the proof can ignore irrelevant propositions, no matter how many of them are there. For example, the proof given earlier, so like this proof, what we have done, not P12 and not P21, this thing, R10, so does not mention the propositions B21, P11, P22, or P31, right? So there'll be some propositions we can just ignore. Like, you see, this one, P11, P22, P31, B21, this one we did not even use the R3. We started from R2. So we can just ignore that part in the tree search, and that will save us a lot of cost. They can be ignored because the goal proposition P12 appears only in sentence R2. So the goal proposition of P12 only appears in R2. See this one here. So, and then the other propositions in R2 appear only in R4 and R2. Okay, see the R4 has that proposition. So you had to use that. So R1, R3, R5 have no bearing. We could completely ignore, we could completely ignore R1, R3, R5 for this particular proof we did. So the tree search will, R1 also we can ignore, tree search will actually be more efficient, right? The same would appear only in R4 and R. So R1, R3 have no bearing. The same would hold even if we add a million more sentences to the knowledge base. So if we add many other sentences in the knowledge base, but still these two sentences, R2, R4 will be the more or the most important part to derive, or the only important part to derive R10 using the inference rules. Okay, so this is important. So sometime, the simple truth table algorithm is bad, although it's simple. Would be overwhelmed by the exponential explosion of model. If I have 200 more literals, there will be all possible combination of the literals. So 2 to the power 200 or something. But this tree search will be much faster to find the goal because it's not even looking at other things. Another property of logical system is monotonicity that I also want to talk. Okay, monotonicity. So what that means? That means set of entailed sentences can only increase as information is added to the knowledge base. So entailed sentence you understand, right? So here, like we already shown that from the knowledge base, we entailed that not P12, right? That's what we prove. All this inference rule just to show entailment, right? Knowledge base, from the knowledge we have, we could say that if knowledge base is true, then not P12 is true. So monotonicity says if you want to show entailment and the knowledge base increases, you have more information on the knowledge base, still the entailment holds, right? Like let's say if KB entails alpha, then KB have some more added knowledge. So this is and KB and beta also entails alpha. Something like, let's say you are in kindergarten and you are learning only A, B, C and all this thing. Okay, so your knowledge says there are 26 letters in the alphabet. Now when you go to the grade 1, first grade, you can now make sentences with ABC also. But does it violate your knowledge that there are 26 letters in the alphabet or any other knowledge you have, ABC? No, it does not. As long as you keep adding to that, this is called monotonicity. Okay, this is called monotonicity. That suppose the knowledge base contains an additional assertion B here. So, okay, that's what. Stating that there are exactly 8 pits in the world for the Umpas world case. Let's say there are 8 pits in the world. Now we gain more information, but this knowledge might help the agent draw additional conclusion, but it cannot invalidate any conclusion alpha already inferred, that not P21 or 12. Okay, this cannot be invalid even if you tell that, oh, there are 8 pits in this whole entire environment or the world. Okay. So monotonicity means that inference rules can be applied whenever suitable premises are found in the knowledge base. The conclusion of the rule must follow regardless of what else is in the knowledge base. The knowledge base can have a world of knowledge. But if you derive some truth, that doesn't mean the truth will be affected if you add some more stuff in the knowledge base. Okay? So next we will learn proof by resolution.